Good afternoon and welcome back to CS240. This is Introduction to Computer Systems. And I want to get started where we left off, though I reprinted it on this sheet so we don't have to go back to sheet 13. Because what we've been going through is we're going to be going through this journey of what level of abstraction do we want to build our apps on top of, and how do we use the different services that can be provided, and how do we build at each different level. And basically what we're going to be doing is we're going to be going through a journey through this chart that we introduced on Tuesday and moving up through the abstraction level and understanding how each level of abstraction works and how we use each one of these levels. So we are kind of right now at infrastructure as a service and containers as a service. So we talked about infrastructure as a service as VMs, and we're going to be working on talking about VMs and containers for most all of today and a little bit into next week, and we'll always be coming back to the lower levels. But as we progress through the second half, we're going to get higher and higher levels of abstraction in our course. So where we're at is we left yesterday as the last thing we said was we said that containers basically provide an isolated snapshot of the exact state of a system at a given point in time. And this snapshot can then be deployed in another system, and that system can run in an identical environment, or as close to identical as possible, as the environment that the code originally ran in. So what this means is you can set up the environment, all your environmental variables, the exact location of the code, every single thing about the environment, you can set up exactly how you want it to try and mimic the environment on someone else's computer. And in fact, that's exactly how the grading is done in this course. We grade with containers. So the container that runs on github.com is the same container I use to grade your code locally on my computer. So the exact same state is used in both cases. And I want to talk about how we can use Docker containers and talk about two different views of using Docker containers, because we're going to get to use both of them. So there's basically two views of a Docker container. The first view is you may be, and as part of this class, you're sometimes going to act as a container developer. So what a container developer does is a container developer is going to create snapshots for others, the users, to run. So the container developer is going to create snapshots for others to actually run. So in the way you do this is you actually create the snapshot by building something called a Docker file. And a Docker file is the exact name of the file that you have to give to build the Docker by default. So this is going to be the first thing that we look at. If we want to build a Docker container so other people can run our program at the exact state that we want to save it at, so they can run with your same environment, your files in the exact same location, everything as identical as possible, we can build a container, or we can build a Docker file to create a snapshot of exactly the state of our system. On the other side of the coin, the second thing we're going to talk about is we're going to talk about being a container user. So a container user is going to use Docker commands to launch Docker snapshots to run. So as a container developer, your primary goal is creating a snapshot of a system. In that role, you're not ever running the snapshot. You're just creating the snapshot for others to run. A container user is going to actually use Docker commands to run the snapshot. And just so we're clear, we're going to call these snapshots, once you have a complete snapshot of the system, we call this snapshot a container image. So container image is the Docker term that we use to say, this is the snapshot that I have of the current system. So I want to first take the view of us as container developers. What if we want to deploy software? For example, what if we want to deploy the web server that you're building as part of MP6 on the cloud? So in MP6, you're building a simple web server using Flask, and what you're doing with that web server is able to take in any PNG file, and then that web server, what is it doing with the PNG file? Once you upload a PNG file, what's your web server doing? Well, so it's ultimately extracting the hidden image, right? But specifically, it's inspecting the image, right? And what is it looking for when it inspects the image? A chunk with the name UIUC. So basically, we're building a web service in MP6 that takes that file that you upload, it analyzes that file at a deep level, at a byte level, and sees if it has a chunk called UIUC. And if it has that chunk called UIUC, it's then going to extract the contents of that chunk and return the GIF file back to the user, right? So that's pretty cool. And in doing that, how many different programming languages are we touching? The server itself is written in Python, yeah. But the service that it's actually performing, the PNG extraction, what is that written in? C. Yeah, so we're crossing multiple languages. We have directories that you have to set up. You have a temp directory you're creating as part of MP6. So you've got a lot of dependencies. It might actually really help. So you don't have to tell a user exactly how to configure everything, how to install C, how to install Python, how to create the directory structure exactly how you want. You might want to set up a Docker to do exactly that. And I wanted you to kind of have some ability to play around with this at this early stage. So I made that extra credit for you as part of MP6. So I hope you do take that on to get a little bit of extra credit towards your grade by actually building a container that runs your MP6. So as a container developer, you're going to have to build what's called a Docker file. And the beautiful thing about a Docker file is a Docker file allows you to inherit a previous snapshot that someone else has built. So the very first line of this Docker file, so this is the Docker file we actually used for MP3. So in MP3, there was this weird issue that Macs were basically not letting us inject the malloc into the system itself. So Macs had an additional level of security that didn't like the way that we were trying to inject a memory allocator into your system. Linux was totally okay with it. Macs were not so great about it. So we were able to create a Docker file that basically gave a snapshot of a system where that system happens to allow us to inject our malloc in there. So that was a hack that we were able to use to get MP3 working with people who are on Macs, so you weren't forced to use EWS. And what we did for that is I said from GCC latest. So the line number 1 is we can inherit a base snapshot or container image to start from. So I had to go out to, you can go out to Docker Hub and see all of the different base container images that exist. One of them was GCC:latest. And this is a container that's set up to have a version of Linux that already has the GCC build tools installed for you. So I don't have to install all the GCC things on my snapshot. Basically, someone's already done the work to set up GCC for me in this container. And then the second command is copy, and that copies files from your computer into the image you're building. So I am copying inside the MP3 directory. I have something called a directory called, so the dot says I'm in my current directory. Inside your MP3 folder, you'll see a folder called Docker, And inside that folder, you'll see a file called entrypoint.sh, which is a shell script that I am saying I want to copy this file into just the root directory inside my container. So in my container, I now have a file at the very root of my container called entrypoint.sh. So this is building up the image. So I took an image that can compile C code, and I said, I'm going to move this entire file into the root of the directory. So now I have a shell file that I can run. The third thing I can do is I can run commands, runs a command in the image. So remember, I'm going to create a snapshot that I'm going to then save that exact isolated snapshot for everyone to use. So to build a snapshot, I might have to run some things inside the snapshot. So the first thing I'm going to do is I'm going to copy over files. Next thing I'm going to do is I'm going to change the permissions, or the modifiers, of the entry.sh and do +x saying that's an executable thing. So go ahead and execute this file. So if I need to install something, if I need to run any commands, I can say run. And remember, this is still building the container. This happens at build time. And then the last thing I put in here is an entry point. And that says, what should the user of the container actually have happen when they launch your container? So when they launch my container, so what happens at launch? So when they actually run your container, I'm saying the thing that should happen is I should run entrypoint.sh. So I'm running the shell script that is in your Docker file. And what this shell script did in MP3 was I programmed it so it just took whatever command line arguments you gave to Docker and actually ran them directly. So you actually did docker run --rm -it, blah, blah, blah. And then you actually went ahead and ran it. So what you're going to do as a builder of a Docker file is you need to imagine the system that you want your code to be running in. You're going to set up that system to be exactly the system you want. So I imagine that I wanted an environment that could compile C code, that took the command that you specified that you wanted to run, and run that command as part of MP3. So you're building up the container. Once you have this Docker file, you actually have to build this Docker file to create the image. And do that, you do docker build, and then you basically give it a tag name that you can refer to it later as. So these were the exact instructions that you went through if you wanted to run MP3 via Docker container. So this builds a Docker file. And these can get increasingly complicated. You can imagine there may be 100 steps that you might need to do to actually build the exact environment you want the end user to have. Because you are basically deploying now a system that is set up exactly in this way, where the file's already been copied exactly to the root directory, and the file has the exact right modifier, and then as soon as your Docker container runs, it's going to run entrypoint.sh. You have basically built a script that says this is exactly what's going to happen on this exact snapshot of a system, and it's going to be as consistent as containers allow across whatever platform you're running on. So it doesn't matter if you're on Mac, on Windows, on Linux. If you run Docker, you've got the same environment. So this is really powerful because you don't have to rely on what's installed on the user system anymore. You get to create your own system inside a container. So for MP6, they don't ever have to have installed Python or C build tools. If you set up a Docker container, you can give that Docker image to absolutely anyone, and they can run your web server. And that's the real power of Docker. All the dependencies are included in this Docker file. You've set up exactly the environment they need on their computer. If they need to run Python 3.9, you're going to use a Python 3.9 inside this Docker. You control every little bit of it. So this is super powerful. This has changed how we can deploy things. And we're going to make a ton of use of Dockers because I don't want to As we build off other people's systems, we don't want to install their entire system. We just want to use their system. We want them to give us a starting point, and we're just going to use their servers or their services through Docker containers. So in fact, in MP7, you're going to be using the MongoDB Docker container. So any questions on how you would go about building a Docker container or the high-level overview? So you're going to get the opportunity to build several different Docker containers throughout this class. Because what you're going to do is you're going to build environments that people can deploy your system by just grabbing the Docker file. Awesome. On the other side of it, you have the users. You may act as a user, and you may want to actually run Docker files. So to run a Docker file, you're generally going to use dockerrun, and then give it a series of potential command line arguments, but eventually you're going to give it a tag. So this is the MP3 Docker we just built above. And just to give you a brief view, so -it, this -I says I want it to be interactive. And -t is on the terminal. So this basically allows you to interact with this Docker. If it prompts you to ask a yes or no question or get standard input, this -it is what I'm going to what I standardly use when I run a Docker container. This lets you interact with it. You sometimes see -d, which makes it a daemon, which makes it run behind the scenes. The nice thing about -it is you can shut that Docker container down by Control-Cing that terminal. If you run it as -d, it runs in the background, and it's going to exist on your system until you shut it down or restart your system. So I feel like as somebody, especially as you're just getting used to using Docker, I find that this is kind of the safest thing. Is doing -it is basically -I -t, and this gives you an interactive window. Docker is going to take over your terminal window, and as long as it's open, Docker's running. But as soon as you Control-C it, you're killing the image. So that's the purpose of the -it. You're not going to see that option all the time, but I would recommend definitely using that -it option, so that way you don't have a bunch of containers that are running on your background of your system when you don't want it to be running. So the second option, -rm, this removes the instance of the image on termination. So as you're running a Docker file, you are going to create an instance of that image on your computer, and the things that a Docker file does, the files it creates and all that stuff, is going to take up space on your computer. If you need to debug the actual run of the file, it's great to have the file system laying around and keep the image laying around. I'm going to guess most of the time in this class, you don't need all the files that the individual image creates. So as you like compile the C code and do all that kind of stuff, if it's within the Docker container, you don't really need that. So -rm just cleans up after itself. And this, again, for the purpose of keeping things small, for the purpose of how you're using Docker containers, it just cleans up after itself. So the idea here is kind of what are the commands that are most useful for how you're going to interact with Docker. And then we get to the commands that are most important. So -b, this mounts your local file system into the Docker container. So remember, as a user of a Docker image, the Docker image gets instantiated. So you have an exact snapshot of the system. Once you're running that snapshot, you're instantiating that system inside a container on your computer. You're virtualizing that environment using process-level virtualization that we talked about on Tuesday. You're virtualizing that environment. And in that environment, you can mount files from your own system. So here, we mounted your present working directory into MP3. So we said inside your container, I want an MP3 directory. so that I can actually run MP3 code. So your code. So what you often did was you may want to make your MP3 file inside a Docker. So we need to mount your present directory that you're running it in into the MP3 directory inside the Docker container. So all -v does is it mounts a directory on your system inside the container environment itself. So the container environment is an isolated environment. Remember, the key idea of Docker is everything isolated. So you're mounting your MP3 into that Docker environment. So this is awesome. Yeah. So it's not creating a snapshot of your system, it's creating a snapshot of whatever system you've built in the Docker file. So in the beginning of Docker file, you're probably going to say from like Python 3.9 or something. So it's going to take the snapshot that someone else built of a Python 3.9 system, and that's the environment it's running in. So your system does not matter anymore once you're inside a container. It's all what you've built inside the Docker file. So a command that we're going to talk about later is another dockerrun command. And here, you're going to see the standard options, --rm, -it. Doesn't matter what order the options are in. You still see these same options that we're going to remove the finished container. But the other really important option that you're going to see used a lot is port forwarding. -p is port forwarding. So that says inside the container, because remember, the container is an isolated environment. Nothing comes in or goes out of the container without you explicitly telling it to do so. Dockers are all about isolation. So if you want that container to allow port 27,017 out of the container and into the container, you're saying from your system, this is the same syntax. What is your system? And what is inside the container? So this is saying I want to mount, or I want to bind, technically, I want to bind port 27,017 from my system to inside the container. So I'm basically creating a tunnel between my system and the container on port 27,017. So now things that are speaking on 27,017 can access your system, and your system can access whatever's on port 27,017. So if you remember nothing at all, remember that Docker is a completely isolated environment that has no access to your system and no access to any external resource outside a Docker environment unless you explicitly give it access. -v is the way you can mount folders. -p is the way you can forward ports. So those are going to be the two ways we're going to mainly interact with the Docker system. We're either going to say, hey, let's mount this directory so the Docker can see some of our files, or we can see some of Docker's files, or we're going to forward a port so we can communicate over a certain port. So it's almost always going to be -p. The same port on both sides is usually pretty conventional, but you could like forward port 80 into some other port inside the Docker container. You can do whatever you want here. But generally, you're going to say same port on the outside and the inside. So Docker's isolated environments, command line options allow you to break that isolation in very explicit ways so you can mount files or forward ports. Then I will always use -it and -rm to make the Docker as friendly as possible. So this is a form of virtualization. We're running an environment that we define in a Docker file on any system that is running the Docker program. And the Docker service is providing that level of virtualization, where it is simulating a system or virtualizing a system based on the exact configuration of the Docker file. When we're running this Mongo, it is configured to run the MongoDB database. Somebody else already figured out exactly what the system configuration is. We just have to run one line of code, and we get a professional database engine on our computer without having to think about anything else. So this is super, super valuable and super powerful. So any questions on kind of what Docker provides? Is it possible to make a container inside a container? Absolutely. There's no reason you can't do it. You're starting to add a bunch of ideally. So I think what you usually see is there's something called, I think, Docker compose, where you actually can compose a file that you have a sequence of containers that all start up simultaneously. Because what you really want to do is you want to create these isolated environments that do one thing really well. So if you need a database and a web server, you can certainly put a database and a web server in the same Docker container. That's two different things that are running. Or you can create a composition where you have a web server running and a container running, and they're communicating internally or through whatever pipe. Does that make sense? So the preference is to actually have two containers running side by side rather than a container and a container. But you certainly can do it either way. Container and container works as well. There's no limit on what you can do. Cool. Any other questions? So we're going to nerd out with Docker a ton this semester. I want to just take a brief second and sort of talk about, okay, now you know about these things. How in the world do you use these things? How do you go about this? When you're making your first startup late over the holiday break, what are you going to be doing? How are you going to be getting these services? So all of these things are, this entire stack from left to right is provided by a whole bunch of cloud-based providers. If you wanted to run a service like MP6, if you wanted to have a Docker extraction on the cloud, you could go and get a virtual machine from Amazon so you can run Docker and your MP6 and your MP2 on it. So you can either get the actual box itself and install the box, or get the box and then run a Docker inside of the box. Either way works. In both cases, you're going to need some sort of a machine. So there's a lot of different, basically every single cloud-based provider provides these same base services when we're talking about low-level infrastructure. Once you get to the higher level system, you certainly, there becomes more and more differences between different service providers. The largest cloud provider out there is Amazon Web Services. This is the one I started using like 8 years ago, and because once you get with one, it's really easy to continue using the same one. So I haven't swapped off that. So this is what I primarily use for most of my projects. And AWS has the most options out of any cloud provider. So if you want just a general purpose computer that has a CPU and memory that you can use to deploy your application, if you just want somewhere to run your code, Amazon basically provides a number of different tiers of technology. So there's 3 current generation general purpose computing tiers. So if you need lots of CPU and very little memory, they have specialized tiers for that. But this is general purpose computing. So if you just need a box to generally do stuff. The very latest is T4G. So even though they're not nearly as good as a PR company as Apple, Amazon is also making their own ARM chips. They're making chips just like the M1 chip. And they're putting those chips into their data centers. So their version of M1 chip is called the Graviton chip. And the Graviton 2 chip is their current generation of their ARM-based chip. So it's just like the M1 chip. It's generally very, very performant, very fast, and generally pretty cheap compared to the offerings, the x86 offerings. So these are anything that's labeled T4G is your ARM-based, Graviton-based processors. Then, even though it's T3, this is still their current generation. If you want an AMD processor, that's T3A. If you want an Intel processor, that's T3. So, and these are all, AMD and Intel are both x86 processors. So depending on the brand of processor you want, you decide what brand you want, and then you decide what size of a machine do you want. And Amazon sells them as access to virtual CPUs and amount of dedicated RAM. So if you said, I want a system that has access to 2 cores and has 2 gigs of RAM, then if you're okay being an ARM device, that's going to cost you 1.68 cents an hour. So in one day, at 1.68 cents, that's about 40 cents a day. So to rent a 2 gig, 2 processor machine from Amazon, it's going to cost you about 40 cents a day. And if you need it on 24/7, like it's a web server that you don't know when someone's going to hit your web service, then that's going to be 40 cents a day times, what, 30 days a month? So that's what, $12? So you can rent that machine from Amazon for about $12. And obviously, if you need half as much RAM, it's about half as expensive. Looking at this first line, so ARM processor, 42 cents an hour. If you go to an AMD processor, it's 47 cents an hour. If you go to an Intel processor, it's 52 cents an hour. So this is what you can do. And you can go to Amazon and you can set up this box in about 5 minutes time. So I've got a ton of these. Most of my boxes are either T3 or T3A. So the tricky part is you have to configure security groups because they want to make sure that you're secure, that only things that can access your computer on certain ports. There's a whole bunch of security settings that it takes to get set up, just like kind of the GitHub.com stuff where you had to make a token, authorize the token. You have to make a public-private key for actually AWS. You have to make sure the public key is deployed in a box. You have to download the private key, set up your SSH client with the private key. There's a ton of security stuff you have to set up. But actually setting up the box, about 2 minutes and a few clicks. Azure is the Microsoft version of this exact same thing. So if you don't like Amazon, if you say, Jeff Bezos, you're evil, I would prefer to support, who's the president, who's the CEO of Microsoft right now? Satya who? Nadella. Okay, Nadella is, if you prefer Nadella to support him instead of Ballmer, not Ballmer was old Microsoft, instead of Bezos, then you can go to Azure. And Azure, let's see, they offer a 2 virtual CPU with 1 gig of RAM for 1.04 cents an hour. 1.04 cents an hour. Huh. So essentially, for the exact same system, you can get the exact same price from Amazon or Microsoft. They pretty much price match each other. When one lowers or raises their price, the other one does the same. So pretty much doesn't matter. So almost equivalent. Google has a very weird and different model. So Google Compute Engine is their product. They say, you know what, we're not going to give you lots and lots of different micro, medium options. We're not going to pre-configure things. We're going to say that you can figure out what you need. And we're going to give you a virtual CPU hour, and that's going to cost you 2.29 cents to basically have access to the virtual CPU. You actually get complete access to it, so you actually get more access to the CPU than you do on Amazon or Azure, but it costs you more. And then you can get RAM for 0.3 cents an hour. So a gig of RAM costs you 0.3 cents. So basically you can get a gig of RAM of storage for about 3 hours and 20 minutes for a single penny. So incredibly cheap. Single gig of RAM, penny gets you 3.5 hours. But if you add it all up, so if you want the smallest unit you can get of a virtual CPU is you can get a quarter of a virtual CPU. So you basically get credits on that CPU. And you can get half a gig of RAM. So the cheapest box you can get on Amazon is going to be about 7.7 cents an hour. Or, sorry, on Google. So you can configure it whatever you want. So maybe you want 1 virtual CPU, a whole virtual CPU, and 4 gigs of RAM. That's going to set you back, 3.5 cents an hour. 2 virtual CPUs, 8 gigs of RAM is going to. So they have these non-custom ones where they pre-configure it for you. So if you want this particular configuration, you can save about, 5% off the custom version of it. So they have a few pre-configured things that if you really want this particular configuration, then you can save a little percentage on their certain predefined ones. But the predefined ones don't start. This is actually the lowest level predefined one. You can't get a predefined box with less than 2 virtual CPUs and 8 gigs of RAM off Google. But the thing is, they're all the same. We're on every single one of these. The big thing to take away, we're always getting virtual CPU time. We're always getting RAM. So we're able to buy a machine. And what you do is you select your operating system, and you get an IP address back. That's it. Then you can SSH into that box just like you SSH into a virtual machine. And we can do that. I can do it live in class if we want to. We can get credits, and you can actually do it yourself. Yeah. Yeah. No, so Campus Cluster is totally different because that's a shared machine where you submit jobs onto a job queue. So that's a kind of older model. When you get one of these, you get a completely isolated box that you can do whatever you want with. So you get root access to these boxes. So you can sudo install whatever you want. So yeah, you're completely isolated in these. Well, Campus Cluster, you have to submit a job, then it runs, and yeah, Campus Cluster is a mess. As far as like figuring out how do you submit a job, how do you do overhead. It's not going to be that isolated environment. Once you do this, you get complete access to the box. So we're going to talk about kind of how you buy these things throughout this semester, because I want you to at least have the knowledge of how to deploy an app. So if you need just a computer to run a web server or run anything you want, Amazon, Google, Azure all offer the service. The service is generally incredibly cheap. The cheapest one runs you like about $4 a month. A box that you're not going to run out of memory in is going to run you closer to like $12 a month. But that's incredibly cheap for having an entire computer. Any questions on AWS so far? This is just one of like, I don't know, 200 different services that AWS, Azure, and Google provides. So it's just like one of their 200 offerings. Cool. If not, I want to chat about this course for a minute before we flip over the page. So midpoint update. So we are almost halfway through the points in this course. We are about halfway through the semester in this course. We're about halfway through the content of this course. So we're really right at the midpoint of the semester. And I wanted to at least spend a little bit of time and see how it's going and give you guys a recap of where you're at. So first, a few updates from me. So one, I've spent the past week making sure the autograder is running the Docker containers, making sure they're as consistent as GitHub as possible. I've made some of the test cases more lenient for you, try and get you as many points as possible. Some of you guys, so like for example, MP3 used to only run week 2 once you pass week 1. And I ran week 1 and week 2 on all of your assignments, which gave you, many of you, points for week 2, even though you didn't pass all of week 1. So most of you ended up with more points on GitHub. There are rare cases where something weird has happened, where you either made a commit as your last commit that wasn't what you want graded, so I grabbed the wrong commit, or in a few rare cases, your code was either hard-coded to actually pass a specific test case. So if I updated test cases even a little way, your code broke completely. And then in that case, I look into actually like how much do you hard code things. I definitely learned that that there's a reason we sort of have hidden test cases, because I saw a lot of people hard code things, which was not very fun. But sometimes when you got a lower score, it's because of that. Other times it's because there was a different pull commit that we saw. And other times it's because you had some sort of memory error. And the program ran differently when it ran in my environment, even though I'm using the same container, as it ran on GitHub. So I want to look, if your score isn't what you expect it to be, definitely, please reach out to me. Because I have emailed back about 10 of you already. And every email I received by 1 a.m. last night, I've replied to. If you sent an email this morning, I haven't seen it. But I want to make sure that you get the points you earned for the MP. And because we're building out this new technology, this is not going to be as robust as anything else. And I'm taking a look at all of your codes. I'm doing this myself. So I've seen all of your programming. I've seen your code. I've seen some really beautiful code that's amazing. And I've seen some okay code as well. But I think that it's great that I'm getting to see your code. That I am really happy to see it when you guys come up with these really clever solutions. That's amazing. So but I have done everything that's on Compass right now, or Canvas, sorry, is what I believe is the correct grades for the work that you've done so far. And if you feel it's not correct, let me know. So definitely check on it, let me know about that. I've done all the grading up to now, so you have all the MPs, you have all your homeworks, you have all the extra credit, everything that's been turned in has been graded. So at this point, there's 470 total points. So that's 70 coming from homeworks. Then you have 6 times 50 for the MPs, so that's 300. You've had 7 homeworks, 70 points here, and then you've had 1 exam. So one thing I do is I believe the extra credit should really be extra credit. So I am taking a look at your grades as they are with raw points. I'm pretending like the extra credit points you're earning do not even exist. So everything you see here is grades without extra credit. And then those extra credit points can just boost your grade even higher. So here is the breakdown of everyone who is in the class. So one way of viewing it is it's hard to kind of scale the grades as they are. So one way of viewing it is how many people have lost 100 points where getting an A requires extra credit. So how many people are basically on track to get an A if they do well in the rest of the course? How many people are on track to getting a B if they do well in the rest of the course? How many people are on track to getting a C? And how many people are on track getting an F? So this is sort of looking at your final points that you have right now and saying how many points have you lost so far in this semester? And of course, this is without extra credit. So if you earn extra credit, you can actually even if you're in the B range, you can get to the A range through extra credit. So half the class right now is in the A range, 49% of people. If you look at your Canvas grade, if you have a score of 370 or greater without extra credit, that's the range that you're in. If you're in the 270 to 370 range, you're in the B range. And you need to do great in the course to get that B, but extra credit can still raise you up to an A, especially if you were on the higher side of this B range. C range is people who have greater than 170 points, but less than 270 points. And if you're in that range, it's going to be very hard. You're really not going to be able, so the maximum amount of extra credit is 100 points. I don't even know if we're going to get to 100 points. Jumping from C to A is almost impossible. So in the C range, you're looking at getting a C if you're staying on track, getting a B if you get some extra credit, especially on the top of the C range. Obviously, if you do worse than you're doing right now, you can fall down that range. And then there's one person who I have reached out to who I think intends to drop the course, but they're still in the course right now. So, but I wanted to be completely fair and basically there's somebody with 62 points in the course. So I don't want to exclude that data point since they are still technically enrolled in the course. I'm not sure why. But there is this one person who is on track to getting an F, but this is sort of where the data is at right now. And I am going to, so at this distribution right here, I don't think that there's right now going to be an adjustment to the final grade points. But I will, because I think this is in range of what we see in similar courses like 234 or 233, 241. If we look at the distribution, so we're like at 50% A's, 30% B's, And I'm definitely aware of this GPA visualization thing that I made. So if we like look at how's this distribution compared to other courses in CS. So like 240, 241, we can see that 46% A's, 21% B's. So it's in line with the distribution that I would the distributions that has been here historically. So I want to make sure that this course is no harder than a course like 241, and the grade points are right in line with this. So I think we're about at the right track right here. So I just want to make sure that you know exactly where you are standing, and you can look at your own grades and your own point total and see exactly where you are on this line. Yeah. Yes. Includes 5, but not 6. Yeah. How many? So this is a new, this is the first time this course has been done in person. So it's hard to know exactly. I think we're, with the extra credit that's coming with MP6, I think we're at like 25-ish points, 20 to 25, somewhere in that range. I will definitely try and, as there's opportunities, I'll definitely keep trying to have the extra credit points. I don't know, I promise, on the syllabus, I'd said you cannot earn more than 100. So even if I offer 150 points, you're not going to earn all of that. I also said it's unlikely I'm going to offer 100. So 50, 60, I don't know. But if we're right now at 20 and 25, halfway through the semester, 50 seems reasonable. I don't intend to offer, whenever it makes sense, I want to offer them. I'm not going to hold back, but I'm also not going to make it just busy work to do extra credit. I want it to be a valuable experience to do it, like building a Docker file. Cool. Any other questions? Any questions or thoughts about everything? So the other thing I forgot that I was going to mention here is I made a mistake. Everything that's due, so in my other course, I have Saturday or Sunday as the big deadline. So I think I was just in the wrong mindset. And you know what's on the website for the due date for this MP6? Sunday. So completely my mistake. But I'm not going to change it because I made a mistake. So that's not the plan. We're not planning on changing them to Sunday. This was just my fault. So they're going to still be due on still going to be due on Fridays normally, but you obviously have till Sunday this week because I screwed up. Yeah. Yeah. Yep. MP7 will be out today and due a week from tomorrow. Anything else? Yeah.
So if you have like 270 points, for example, if you get every single point after that, then you're on track for a.
If you get all the points and you're at 270 exactly, if you get 1 point of extra credit, you're actually going to get an A-. If you earn the point, all the other points. Yeah, Lloyd.
Are you still posting video lectures?
Yeah, I'm going to. Yeah, so video lectures will go up as soon as, it's sort of the lowest priority item in the things I'm doing for you. So I'm going to make sure the MPs are great, because I'd rather you guys hear. It's more fun here. I think that the video lectures are a great supplement. I make sure they're all up before the exams, for example. I'm probably going to, I think I have a log of 2 of them to do right now, so I'll probably grind through all of them this weekend. But I make sure to and let me know how, I've been kind of cutting them, making sure they start right at the beginning of class, ending at the end of class, so that it's a nice, clean, video. Let me know if that is good, bad, if they're useful. Yeah. Is there a final exam? So there is not a final exam per se. So if we look at the rest of this course, we have one more. So we've got one more exam that's coming up in week 15. And then, so you have exam number 2, and that's going to mainly cover the Act 2 part of this course. And then the final exam period for this course isn't an exam, but it's going to be the final project. I don't know when. Yeah, I don't know what the final exam. I need to look. I haven't seen. Is it the 10th? Oh, so we have that first Friday. Okay. All right. Well, then we're going to be, yeah. So if I'll confirm that and send it out in an email. But I assume if that's what the schedule says, do you remember what time it says? 7 and 10 p.m. Okay. So yeah. Then, yeah. So 7 and 10 p.m. then on. $240. Yep, 7:10 p.m. in 2035 in this room. Perfect. Yes. So that will be our final exam or final project time period. So the final project in this course, because we're working towards building web services, right? So basically what you've done up until now is you've been on your own building systems that work on your own computer. And now we're slowly building web services, like in P6, where you're actually accessing it via a web browser. So the final project, I want us to build something where we each build something individually, but then as we have all of our things running in this room, we can have something that connects to multiple different machines to complete a task that no one machine completes on its own. So I want to build something that is a microservice-like architecture that we actually utilize multiple people's programs to accomplish one task. So that's going to be the final project, where we're going to work as essentially a large company together. And we're all going to build pieces of a service that we're going to run together on the final project day. So we're going to all be here in this room, making it all work together. Yeah. So is it group or individual? That's the one thing I haven't quite decided yet. So I think part of it's going to be deciding how it's scoped out. So I'm trying to figure out exactly what I want this thing to be. Like I'm kind of thinking, so we could go along with the theme of making agents where each agent kind of works towards a common goal. That's more individualistic. The other thing is doing some like machine learning or like processing using like some Python APIs to do like machine learning or image processing or segmentation. Then each group does like a piece of a pipeline where basically we might give it an image and have different ones of you become experts in different services. And at the end, we get like a huge recognition. And each one of those services are only like 10 lines of code by themselves. But because we're each doing something different, we eventually get something that can do a whole bunch of things to a single image because we're using all of our services together. That'd probably be more group-based. But I haven't quite, I'm working with the TA and the staff to figure out like what makes the most sense, what's the thing that we can give you the most support in office hours for. Because I'm a little worried, I'm the only one on staff that really knows a lot of AI. So even though I think the AI project's interesting, if we don't have the staff to kind of make sure that you can come to office hours, that's going to be a bad experience for you. So I've got to make sure that it's the right balance of stuff, that I'm not the only one that can support you, but we have a whole team to support you. So we're still trying to figure out the exact details of the final project. Hopefully that helps. So, but the big goal of the final project is I want us to really build applications that are using multiple people's computers in the same room. Any other questions? Cool. Okay, then if not, then let's talk about the back half of this lecture. And let's talk about data stores. So just like we kind of talked in the very beginning of the semester about data, the key idea of data is going to exist in every application we build. So in the beginning, we looked at hexadecimal. Don't worry, we're not going to go back to hexadecimal. Instead, we're going to talk about different ways we can actually store data on a program and think about how the different ways we store data influences our program design. So the first option of storing data is something you've done a ton of. Ever since you probably programmed your first program, you can always store data in memory. So the idea is use program variables and data structures to store your program's data. So this is what you've done. So the big idea is you use program variables and data structures to store your program's data. So this is what you've been doing probably for your entire programming career. Most of what you've been doing is you've always been, if I want to store data, I'm going to create a variable. That variable might be a dictionary, it might be a linked list, it might be a tree, it might be a graph. You're storing data locally on your own computer in memory using a data structure. So the examples is all of the code you've written. Certainly all of the code in 240, I think all of the code in 225, I think pretty much all of the code in most of your other courses are in-memory data structures that you create by variables within your program. It's easy, it's simple, it's straightforward. You control the entire universe. But you're now limited to just your program. We want to build cloud scale applications. We don't want to be limited just your single program. What if the two of us want to work together on building something big? That's not going to work if I have my data structure and you have your data structure. We want to share data somehow. So once we think about cloud-based systems, we've got to think of different ways to store data. And the first kind of option is sharing data, and the option that you may have used before, and the option you often use to transfer data between programs who are offline, not online API programs, but offline programs, is file-based storage, or file-back storage. So the idea is you use a file or data stream to store the contents of your program's memory, of your program's data. So the idea is to use a file or some other data stream to store the contents of your program memory. So this is often seen when you have like a CSV file or a JSON file. You have a file-back storage where basically the way you transmit data from one program to another program is you actually just save a file and you save it in a specific format so the other person can read that file and get that data. This is great for scripting environments where you might have multiple stages where you're scripting like, okay, I'm going to process this, take in the CSV file, process it, output it as a JSON. So there's a lot of pipelines that say, okay, I'm just going to make one program that does one thing very well. It's going to read in a file. It's going to output a second file. If you have kind of batch systems, this is a very, very common workflow. And I'm guessing you have probably seen at least some of this. So you guys were around in the 120s. Wait, did any of you take 126? Is that a thing any of you took? Okay. I believe, this is a rumor I've heard. I actually don't know the 126 syllabus very well. But I've heard like literally half the class is JSON processing of files. One MP, two MPs? It wasn't crazy though. Okay, I think I may have scaled it back or somebody told me a big lie. But you've done some JSON processing, right? Did you have to parse it yourself or did you get to use a parser? You were able to use a parser? Yeah, so many of you have actually seen this file back storage, this idea that you can take a CSV file, take a JSON file, load the data in via these files. So this is great, except for someone has to write the file, you have to know the file's written, and then you can read the file. Instead, when you start thinking cloud-based applications, you are generally going to start thinking about how do you actually store data in a way that any instance of your program running can access this data. So one option to store data is in what's called a key value store or key value storage. So the idea is to have an API to a dictionary-like interface with key value storage. So what key value storage means is I give you a key, and you return me the value that's stored for that key. And that's as simple as it is. So if I'm storing the value, so I might have a key value store, and in my key value store, I say WAF, I might do, or if we're going to use Python syntax, key value store.get of WAF, and that might return Wade, because my net ID is WAF, and it might return Wade. So basically the key in the system is a string, and then the value is either a string or an object, depending on what kind of system you're in. So the idea is you index everything as a key, and that key then returns you back the value that's been stored. So the entire interface you have is you just give it a key, it returns a value. That's all you get. You don't get complicated data structures, you simply have a key value store. So if you got to store a certain piece of information, this is a great system. And you can be very, very creative with your keys. This seems very flat, but I've programmed a lot of systems that use key value stores because key value stores are insanely fast. You all know about hash tables and how efficient you can make a hash table. So what you can do is you can basically have like a string that is like your user ID dash, I don't know, if you're making a game, maybe you have money. So your key can be user ID dash money, and now that's a unique string that identifies a particular player with a particular ID number and the amount of money that player has in that game. So even though it's a very flat space where you have to have a unique key, it's not very hard to figure out how to create a unique key for every single user in your system. So obviously this only works as long as your data is very flat. As soon as users have lots of different fields, this gets very, very complicated very fast. But it's extremely fast, so if you just want to be able to look up a key and get a value back, key value stores are great. There's a system called Redis. This is the largest open source key value store tool out there. And you basically you can connect to a Redis server, it does the key value store for you. So that means it's not in your memory anymore. It is stored in the cloud at an address that you contact. And the Redis storage is going to remember your key value pair. This is particularly great for things that you need to cache. So if you know you might be looking up something again and again, and you want to quickly access it, you can store it as a key value pair and basically check, oh, okay, is this key in my dictionary? If it is, just return what's in the dictionary, otherwise actually do the work to look it up. So now your data is not in your memory, you're actually making a call, a get or a set call, to put something in a store. So if you need a little more complexity, you don't want just a key value pair. What if you want to store an entire dictionary inside of a cloud storage mechanism? So our fourth option is document stores. So these are sometimes called NoSQL databases. So the idea here is store and search entire objects, say JSONs essentially, in the cloud. So what this means is that I actually give it an entire dictionary, an entire JSON. So I might say that like one and we call these documents. So one document may be that my net ID is WAF, my name is Wade, and my sign is I'm a Sagittarius. So what I can do then is I'm storing this entire dictionary. And what dictionary data stores allow us to do, it then allows us to query any specific field in this dictionary and get back all the records that have that field. So now I can ask the data store, I can actually ask it to find one where the net ID is WAF. So it's going to find one record where my net ID is WAF. I can also find all. I can say data store.find all, where the sign is Sagittarius. You can find everyone with late November and early December birthdays. So we can now query any particular element inside of this JSON. So now each user can have a complete user profile, and as long as we represent it inside of an object, a JSON, then we can query this JSON and say, I want to find an object based on any individual field within this object. Not everything has to have all the fields. You can actually query if a field is blank or a field is not blank. But the whole idea is we're going to build a database around the idea of documents, where documents are objects, and we can ask about the fields of any single object. So this is the most popular form of database for small web applications. You can literally just throw whatever keys and values inside a document, all of that stays together, and you can query that document based on any field within that document. So the open source technology that is most widely used is a technology called MongoDB. So MongoDB is a document storage solution that exists in the cloud, where your program connects to a MongoDB server, and then your program's data is stored as dictionaries inside the cloud that you can query just like that. So this is another way to store your data. So this basically gives you like an object-like storage inside of the cloud. So now we've got another way to store your data. Fifth way to store your data is a relational database. This is like Postgres or MySQL. So these are all your SQL databases. So this is a relational database is a highly structured relational table storage. So highly structured relational table storage. What that means is that you might have a user table, and your user table has a net ID field, a UIN field, a name field, and then every single record inside the user thing has exactly these fields, and every single piece of data has to have a record. You have to create what this table looks like beforehand. You can't just throw additional things in it. You have to use a specific language called SQL to interact with this table. It's extremely fast. It scales to millions and millions and millions and millions of records, but it is a lot of complexity. It takes a lot to start up a database. You have to figure out exactly what your database table design is. There's entire theories on database design. For a general simple application, SQL is almost always overkill. SQL works great if you have millions and millions of records. So if you have less than 1 million records, I would really think about if SQL is the right technology. The thing about SQL is SQL's been around forever. Like, see, I don't even remember a time where SQL databases don't exist. So SQL is super powerful. It's super well known. It's a tool that people reach for. But it has a lot of complexity. It's got a lot of constraints. If you're really interested in it, there's a great course called 411, CS 411, that goes all into mostly SQL databases. You'll learn all the relational calculus and all the theory around that. So we're actually not going to spend much time on relational databases, because if you need a very, very highly structured environment, you can make relational data. You can use relational databases. So the last option is there's a lot of individual data stores that can happen, or a lot of specialized data stores. So there are things like a graph database. So if you have a graph data structure and you want to build a graph database, there are specialized graph databases that talk in nodes and edges. So so that like Neo4j, 4G, I think. Neo4j is a database engine specifically designed to store graphs. It speaks in nodes and it speaks in edges. So that's going, if you have graph-like data, don't map it to a MySQL database or have a bunch of nodes in a Mongo database. Like if you have a graph data structure and you're going to ask questions about graphs, you want a special purpose tool that's designed to store graph-based data. So if you're Facebook and you have a social network where a lot of what you're doing is graph queries, you're going to want a specialized data store. So if you have a very specialized data structure, you want a specialized data store. Geographical information is another one. If you have a bunch of GPS coordinates, and you want to know how close two things are together, there are specialized databases for that. There's specialized databases just for text querying. So there's a lot of specialized data stores that you can use if you have particular questions about your data and want to optimize your programming flow around those questions. So these are all different ways you can actually store data. You're no longer storing data in memory once you're past the first one. Now you're using cloud-based solutions to store data in different ways. So in MP7, you're going to explore using two different forms of data storage. You're going to start out building MP7 just like you've built every single MP you've built in the past. And you're going to build a web API that's actually going to store a data, just basically a simple key value store, essentially. So if I say you should store the NetID, if I say for the key WAF, you should store the name Wade, your program's going to remember WAF corresponds to Wade. And we're actually going to make you do a version data store. So if I overwrite WAF and say now WAF stands for like my wife, Kiri. Now version 2, the current version is Kiri. Version 1 was WAF. So you're basically making a version data store where you're keeping a history of the versions we had. First part of MP7, you're going to do exactly that. This should be very straightforward. You know how to store data. Second part of MP7 is I want you to actually not store data yourself, but instead store it in a database so that any version of your program, no matter where it exists on the internet, could actually access your database. And you're going to use the MongoDB interface to do that. So what you're going to do is you're actually going to run a dockerrun command to start up the Mongo database. That's all you need to do to install Mongo. You don't have to install Mongo yourself. Mongo is going to be running in a Docker container. So your program will connect to that Mongo instance. Somebody else has already done the work to figure out how to run an isolated environment of Mongo for you. And then what you're going to do is you're going to interact with the database. So you're going to have a database that is a data store, and you're going to get like a collection, like if you call your database 240, and that's why you want to store all your 240 objects, then you're going to be able to do on your collection, insert one. And whatever key value store, any other metadata you want to store with it, you're going to insert it into a dictionary by just using a JSON. And instead of putting it into your own memory, you're going to be using that call to actually write it to the cloud. And that's going to store that data in Mongo. Then when you want to go out and find it, maybe you call your key name, maybe you call it key, maybe whatever you want to call your key name. If you want to find Wade, well, if you just inserted Wade for the name Wade, it's going to find the record for name Wade. So now that I've found this record, hello, I can see that it will also return hello world. So you have this collection where if you store all the different versions in the same dictionary, you're now able to say, oh, I want to grab version 1 of this or version 2. So you can decide exactly how you want this interface to work. You basically have this ability to insert a dictionary into a data store, get that dictionary back, and you just have to design an API that you keep a track of all the versions of data that we sent you. So as we send you keys and ask you for the values back, you're going to first completely program it using just local storage, and then transform your program using MongoDB so you're no longer storing data on your own computer. You're actually using cloud-based technology to store your data so you can run multiple versions of this app all talking to the same database. So that will be out tonight. You'll get to play around with this data store, see how you get to use a Docker container that someone else built to build Mongo databases for yourself. I'll be here for a few minutes after class if you have any questions. Otherwise, congratulations on doing so well this semester. I hope you've already learned a lot. If you have any questions, I'll be here. Otherwise, have a fantastic weekend, and I'll see you guys on Tuesday.